Okay, so on the lab that I just gave back, the one where you had the Atwood machine, which is the pulley, okay? And so here's what, you got a pulley here, right? And let's say you've got the 220 gram mass here, and then the 200 gram mass over here, okay? Every one of these problems, every one of them has the exact same idea. We just tweak the idea a little bit, but it's the exact same concept every time. When you let go of this and you see something accelerate, as soon as you see something accelerate, you know two things. You know that the net force does not equal to zero, okay? That's what you know. There's an unbalanced force. Okay, that's one thing that you know. The other thing that you know is that the only way that can happen is one of two ways. Either there's only exactly one force acting on it, or if there's more than one force, the other force has to be less than the force that's making it accelerate. Okay, it's the only way that can happen. So what we did is we said, okay, to make this simple, we're going to stick with this same thing. The force net is going to equal force applied plus force opposing. So we said, okay, we're going to call this the applied force because that's the direction that it's going to move in. So all you had to do to get that applied force is take 0.220 kilograms times G, and you get like 2.2 newtons. Okay, it's about it. It's about 2.2 newtons roughly. Now, here's what and this comes down to a question that a lot of you missed down below. Down below that section on the lab that I just gave back, I said, okay, if we cut this string on the other side, in other words, instead of dragging the 200 gram mass, if we just cut that string, how would that impact the applied force? And what you have to develop is the ability to figure out what is important in terms of a calculation, what variables do you need, and what isn't. So if you look at how you calculated that, what we call that applied force, all you did is you took the bigger mass and you multiplied it by G, okay? So the mass that's on the other side had no bearing on that whatsoever, okay? That was not part of the story. The applied force is only determined by the bigger mass. When you let go of it, that begins to accelerate. This side over there, that 200 gram mass, wasn't part of the story, okay? That had no bearing on it. Now, did that opposing force affect it? Yes. That's why that's taken into as an opposing force, which decreases your net force, which decreases your acceleration. So the applied force in and of itself doesn't change, okay? Because it's that mass that's going to fall. Now, we rolled that same idea into the lab that you all did yesterday, okay? So if you look at the lab that you all did yesterday, and if you look on this back question, okay, and on question number 10, so let's talk about number 10 on the back side of this. And there's a reason that I chose those specific amounts, okay? So on question number 10 on the back, I said, okay, we're going to put a 200 gram mass on the end, and we're going to drag a 220 gram mass that's up on there on the table, okay? Now, here's the story. In this situation, since the 200 gram mass is on the end of the string, right, it's going to drag the 220, okay? That's what's going to happen. So if you look at, and I promise you, on this test, coming up on forces, there is going to be a problem just like this. All I'm going to do is change the numbers, okay? Swear to you, it's going to be like this. I swear to you, okay? If you really want to start studying for this test, because it's going to be the biggest test, make a set of index cards that says, oh, okay, hey, what happens when I have a mass suspended from the end of the table? This is one of the types of problems that you've got to be able to do. Okay, well, here's the difference between having the 220 suspended on the end of the pulley and the 200 gram mass versus the 200 gram mass and the 220. So what I want you to see in both situations, the same mass is involved. There's a 220 and a 200. Same mass is involved, exact same masses. But here's the difference. With this one, the 200 gram mass is going to fall, and the 220 is going to get dragged along with it. If it's suspended over a pulley, the 220 is going to fall, and it's going to drag the 200 up. Okay? And here's the difference. This one, there's a table. Okay? That table is preventing gravity from making that 220 fall. So that's going to be one of the questions down below. On question number 18 down below, it says, regarding the trials with the track, why didn't the weight of the cart on the track act as an opposing force like it did in the Atwood machine? And here's the fundamental difference, is that when you put this thing up there on the table, gravity is still pulling it down, but the table is preventing that from falling. Whereas if you suspend it over a string with a pulley, there's no table to prevent it from falling, and the 220 is going to fall and it's going to drag the 200 up. Hello?
One, can you excuse my absence since I'm with FFA?
Yeah.
Two, does anyone want a burrito?
What flavors do you have?
Bacon, egg, and cheese, and sausage, egg, and cheese.
You have no egg and cheese?
Oh, we do, but they're down in the MTA.
That's okay, don't worry about it. But yes, I can. Does anybody want a burrito? Going once, going twice?
Yeah.
$4?
They're $4. We have cash on hand though.
Okay.
Which one do you want?
They're really good.
You want sausage or bacon? Thank you. Yeah, Devin.
Oh, the floodgates have opened.
Yeah.
Angel, you started to trend.
Anybody else? No? Okay, thank you guys.
All right.
I'll be here when we get done.
Okay, back to our story. Back to our story. So, when you get to, let's go back to question 10. And you want to calculate the acceleration. So here's the story. Let's talk about what would happen in two different scenarios. Scenario number one, we just cut the string. So this is the one you're suspending the table. So gravity is pulling down with a certain force. If you take 0.2 kilograms times G, you get 1.96 newtons. Okay? So gravity is pulling down with that amount of force. Okay? We're going to let gravity do this because we know gravity provides an exact amount of force. I know exactly 1.96 newtons of force is going to be applied. Now, scenario number one, I cut the string. Okay? I just cut the string. It's not dragging the mass that's up on the table. Jaden doesn't have to take along her little brother. Okay? We just cut the string. Right? So if that's the case, that 1.96 newtons is the only force acting on it. That is the net force. Okay? There is no opposing force. There's no mass that you're dragging with it. Nothing. And if you take 1.96 newtons, and oddly enough, if you divide that by 0.2 kilograms, you get an acceleration of 9.8 meters per second squared, because that's the only force acting on that mass. Okay? Now, the string is attached. That 1.96 newtons is still my net force. Okay? That is still the net force. That's it. But here's the difference. Number one, there's no friction, anything like that, so there is no opposing force. But what happens is that it has to drag that mass with it. Okay? So since it has to drag that mass with it, we divide always by the total mass of the system. So to get my net force, I'm not 1.96 newtons is not only accelerating the 200 gram mass that's at the bottom of the string, it's also accelerating the 220 gram mass that's up there on the table. Okay? So we're going to take the 1.96 newtons and we're going to divide that by the sum of the masses. Okay? Now if you look at what you just did, and this is this answer to number 11. So in a problem like this, you want to drive, hey, how can I work any problem like this? Okay? And you did this like 3 different times in the course of this lab. You took the mass that was hanging from the end of the table, maybe you call this mass 1, mass Bubba, mass Leroy. I don't care. Okay? Mass Red. I don't care. Okay? You're going to call that a certain mass. And you're going to multiply that by G to get the force that's going to make the system move. That's it. Then you're going to take that number and then you're going to divide that by the total mass of the system. Okay, that's it. So no matter how these problems play out, whether I put the 220 on the end, the 200 gram mass up there, I put an elephant on the end of the string, I put a giraffe up there on the table, which would be really awkward, but you'd get the point. Okay? So it doesn't matter. Every problem like this works the same way. You take the weight of what's hanging from the end of the string, and then you divide it by the total mass. That's it. Boom. There you go. Okay? Now, when you get to question number 12, here's how we're going to change things up on number 12. It's the exact same mass, right? I still got the 200 gram mass on the end. I've got the 220 gram mass up here. Now, realistically, in any situation, there's a little bit of frictional force, okay? So number 12, you want to figure out what's going to happen in terms of that frictional force. So here's the deal. The 200 gram mass has nothing to do with that frictional force. The only thing that determines the value of that frictional force is the interaction between the table and the mass that's on top of it. The 200 gram mass, not part of the story. Okay? It's not, doesn't matter. Okay? Does not matter. The frictional force is only determined by that relationship between that block that's on the table and that coefficient of friction. So when you get that answer to number 12, that should be around 0.3 newtons. Okay? So your answer to number 12 should be around 0.3. So here's what we're saying. In round numbers, in very round numbers, when you let go of this, you have a force of about 2 newtons pulling this thing down. You have a frictional force in the opposite direction of about 0.3 newtons. So you have a 2 Newton force trying to make it pull, created by the gravity mafia, and the frictional mafia is going, whoa, 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 we don't want to go, okay? So this is the one time where the two mafias actually interact. You have the gravity mafia pulling it down to 2 newtons. The frictional mafia is working against you at 0.3. So what's going to be the net force when you apply a 2 Newton force direction in a 2 Newton force in one direction and a 0.3 Newton force in the other? What's going to be, what's left over? About 1.7 newtons, okay? So then you're going to take that 1.7 newtons, about, okay? And then you're going to divide that by the total mass of the system, which is going to be that 0.420 kilograms. And you're going to get an acceleration of about 4 meters per second squared. So here's what I want you to look at, okay? Your answer to number 10 should be about 4.5 meters per second squared. Your answer to number 13 for that acceleration should be about 4 meters per second squared, okay? And it's less because of the fact that you have a smaller net force because you have friction acting in the opposite direction, okay? Now, when you get to 14, okay, and this concept of an Atwood machine. So when you get to number 14, here's the story. Again, it's the exact same masses. I got 220 on one side. I got 200 on the other. Now here's the difference. When you set it up like this, the 220 is going to fall and the 200 is going to go up. But here's what's different. Now we don't have the table. So even though they're the exact same masses, and I was consistent, this is why I always had the same masses, so that you can see the difference between them. If I got a 220 and a 200 hanging over a pulley, the 220 is going to fall, the 200 is going to go up. But if I put a 220 up here on the table and a 200 on the end, the 200 is going to go down and the 220 is going to get dragged along. Okay? That's why I picked those specific numbers so that you see, wow, in one situation the 200 gram mass will fall, in the other situation the 200 gram mass is going to go up. Okay? That's what I wanted you to see. Now, there's an intermediate step. And this is what happened over here on the third page of the lab. Third page of the lab, I said, okay, hey, we're going to put this thing on an incline, and that's the basis of what we're going to talk about today. So, again, you have to develop the ability to look at what stays constant and what changes. So, when you put that block underneath here, the 20 gram mass was still being pulled by gravity, and that's what we're calling the applied force. So when you get down to question number, of those questions down below, I said, in comparing the track to the incline, how did the following change? I said, explain your answers. I said, the applied force. The applied force didn't change because it's still the same 20 gram mass being pulled down by gravity. Okay? It didn't matter. So if you look at how you calculate that applied force, it's the mass at the end of the string multiplied by G. That's it. Okay? What you're dragging has no influence on that calculation. It's only the mass that's at the end of the string. Then, now, here's what's different. Now you have a force that's acting in the opposite direction. Now that's impeding that motion. Now you have an opposing force. Now that decreases the net force, and therefore you end up with smaller acceleration. Okay, so that's what I wanted you to see. Okay. Anything you want me to explain beyond that? At all? Any question you go, hey, maybe my answer is right, maybe it's wrong, I don't know. Anything at all? Make sure on number 9 on page 2 that you have explained why everything is false and none of that is true. Okay? We're good? Absolutely good. Going once. Going twice? What?
14.
14? What's the value of the applied force? Okay, here's what you can do. Jaden, that's the 240. And then you got the 200. Okay? So, what we're going to call the applied force is that 2.40 kilograms multiplied by gravity. We're going to say, because that's what's going to make it move. So, on a situation like this, your applied force will always be the bigger mass multiplied by G. The opposing force will always be the smaller mass multiplied by G. Okay? All right. Anything else? Going once? Going twice? So get those handed in. So stop that computer for a second. Okay, so today we have our last big topic of forces, and that's inclined planes. So, in Kansas, inclined planes really aren't that relevant because we live in a very flat state. Matter of fact, somebody had way too much free time, but they did an analysis, like if you compared Kansas to a pancake, like on the same scale, okay, Kansas is actually flatter than a pancake. Like on the same scale, a pancake has like little air bubbles and everything. A surface of a pancake is actually more, or less flat than Kansas is. So, yeah, that's just what we have. Okay, I'm just telling you, somebody was really bored. All right, So you all kind of intuitively understand inclined planes. I just have to get you through the math. So what I have here is your basic track that you all work with, okay? And I'll put this on here, okay? And if it's completely level, like this, okay? Feel like I'm doing yoga. Okay? So when it's flat like this, like that, are there forces acting on the cart?
Yeah.
Yes. But why isn't it accelerating?
Net force is zero.
No.
That force is zero, all the forces add up to zero. Is gravity pulling it down? Yes. What's the track doing? Pushing it up. Now, even if I move it back and forth like this, you notice that pretty much just stays, which is kind of cool to watch. So, why does that cart pretty much just stay right in front of me? What does the cart have? Inertia, because it has mass, right? It wants to remain at rest. Now, if I flip that thing over and do the same thing, well gravity. Okay, we'll use this one. Okay, so if sorry, gravity took over. Speaking of unbalanced forces and acceleration, that just happened. Now, if I do it like this, why does the cart move with me? But if I do it with the wheel sides down, the cart stays in the middle. What's the difference, Carson? Huh?
Friction.
Friction. Which case do I have more friction? Wheel sides down, wheel sides up. Up, okay? It's the exact same mass. I haven't changed the inertia, okay? It's the exact same mass. If so, has the exact same tendency to remain at rest or the exact same tendency to remain in motion. Okay. Now, if I take this cart, when it's flat, and it's going to stay right there. But if I give it any tilt at all, what does it begin to do? It begins to accelerate. So right away, as soon as I tilt it, right, it begins to accelerate. As soon as you begin to accelerate, what is your net force not equal? Zero. Now, if I were to ask you to draw a graph, even though we haven't done any calculations, but I'm going to have angle here, okay? 0 degrees, 30 degrees, 45 degrees, 60 degrees. And then way out here, I'm going to put 90 degrees. And then here, I'm going to have the acceleration of the cart, okay? So at 0 degrees, flat surface, okay? I put the cart on here at exactly 0 degrees. What's the acceleration of the cart? At 0 degrees, come back here. 0, right? Okay? Now, at 0 degrees, I have no acceleration. Okay? It's flat. Now, as this thing goes, if I lift this thing just a little bit, I get a certain amount of acceleration. If I lift it higher, I get a bigger acceleration. So what's that graph going to look like? So as the angle gets steeper, what's going to happen to the acceleration?
Greater.
It's going to get greater, right? Now, if I go to an extreme case of 90 degrees, okay, I go to 90 degrees, I let go with it. What's going to be the acceleration of the cart? 9.8 meters per second squared. Because all of that force is going to be acting straight down, I'm going to get an acceleration of 9.8 meters per second squared. So this graph is going to start here at 0, 0. At 90 degrees, it's going to be at 9.8 meters per second squared. So this graph is going to go something like this, okay? So the steeper the angle, the greater the acceleration is, right? Remember that if you ever drive like up in the mountains. Oh, okay, right. Hey, I'm up in the mountains, steeper angle, wow. That's a bigger acceleration. Same thing is happening if you ever go skiing. Like, oh, we're going skiing over spring break. you remember this graph, okay? The steeper that mountain is, the bigger the acceleration is gonna be when you go down it. Okay, so you got this, all right? Now we just have to figure out the math. So when you look at the forces, because fundamentally this is what's gonna happen. When you have an inclined plane, so let's say that we're gonna put a box with a mass of 1.02 kilograms on this inclined plane. And let's say that's at 30 degrees, okay? So when you have an inclined plane, there are three forces that always occur. Always, 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 no exceptions. Whether there's friction, there's movement, doesn't make any difference. If you have an inclined plane, there are always three forces. One of those is gravity, which is going to act always straight down. Okay, so gravity always acts straight down towards the center of the earth. Same calculation that you've always done. So in this situation, if I want to calculate the gravitational force, I'm going to take the mass of 1.02 kilograms times 9.8 meters per second squared, and I'm going to get 10 newtons. Okay? Trust me, that's what you're going to get. Now, do not worry about making that positive or negative. Okay? Just always make it positive. Because the only thing that we're going to do with that 10 newtons is use it to find the other forces. So the 10 newtons is like a gateway force. Okay? We just use that as a way to get to the other forces. So do not, when you calculate the weight, just get the number. Okay? Don't worry about, oh, do I make weight negative or pi? Oh. Just make it positive. Because the only thing we're going to do is use that to get some other numbers. Now, in terms of vectors, there's two other ones. Now, I'm going to show you two ways that you can draw this. I don't care how you draw it, it's up to you. I'm going to show you both methods. So the first one I'm going to show you is more true to the geometry. Okay? So the other forces that you're going to have, one side is what we're going to call the normal force, which we've dealt with before. Okay? And then the other one is going to be, come on, the force parallel. Okay? And that makes a 90-degree angle. So let me draw that a little bit bigger so that's a little bit more clear. So you got FG, force normal, and then force parallel, and this makes a right angle. Okay? Now, what you will always know is the gravitational force. So as long as you have mass, you can calculate G. Okay, you know what G is, multiply the two numbers together. So FG is going to be just like you've done before. It's just going to be mass times your gravitational acceleration. This isn't anything new. It's a calculation you all have done. Feel good about this. No worries. Now, without going through a whole bunch of geometry, whatever angle the inclined plane makes with the ground is going to be the same angle that this is in here. Okay? You don't have to subtract 90. It isn't complementary angles. It isn't half. It doesn't make any difference. Okay? Whatever angle this is whatever angle this is. So if you go with this example, our weight was 10 newtons, and we said that's going to be a 30-degree angle. Okay? If it was a 45-degree angle, I'd use 45. If it was 60, I'd use 60. Okay? So at this point, you're going to know the hypotenuse. So the hypotenuse is the side of the triangle. That's the number that you're going to know. You're going to know the hypotenuse. You're going to know the angle beside that. Okay? So you're going to know the hypotenuse and you're going to know an angle. So let's talk about force parallel first. Okay? So which trig function can I use, knowing the hypotenuse and the angle, to find the side opposite of that 30 degrees? Devin Walter White.
Sorry, I don't really, could you repeat that?
I can. I know the hypotenuse, which in this case is like 10 newtons. Okay? I know the angle up there is 30 degrees.
Mhm.
So I know the hypotenuse and I know the angle. And I'm trying to find the side opposite that angle, knowing the hypotenuse. So which trig function am I going to use? Sine, cosine, or tangent?
Sine.
Sine. Fantastic. So the sine of the angle is going to equal that side opposite, which is force parallel, divided by the hypotenuse, which is my gravitational force. Okay? So in this situation, to get my force parallel, I'm going to take Fg times the sine of the angle, and that's how I'm going to get my force parallel. So if you look on your big dog equation sheet, I give you this equation. Force parallel equals Fg sine theta. And the reason that is force parallel, sine theta, to use sine, is because it's the side opposite of that angle. Okay? Now, Devin, now let's talk about force normal. So if we use sine to get the force parallel, which trig function am I going to use to find the side adjacent?
Cosine.
Fantastic. So if I look at the cosine of the angle, which is going to be force normal over Fg, then my normal force is going to equal Fg cosine theta. Now, remember way back when we started this unit, okay, we had the very first lab, and you were pulling things, right? Little blocks of wood, right? And I said, this is technically how you calculate force normal, Fg cosine theta. This is where that comes from, okay? Now, up to this point in time, in your esteemed physics careers, every surface has been flat. Okay? Every surface has been flat. Now it's not. Now we have to worry about that cosine theta part. Okay? So up to this point, the angle has always been 0 degrees. Cosine of 0 is 1. You didn't have to worry about it. Now you have to worry about it. Okay? So anytime you have any kind of an angle, when you calculate force normal, you have to worry about the angle part of that. Now, I know you all sit there and go, oh, Mr. Burkamp, we won't forget that. We'll always take the angle. And no, you won't. You lie. Okay? I'd like to think you don't, but you're going to. But I swear to you, just when you calculate that force normal, get out of this habit that, oh, it's just the same as gravity. It's not, because we're on an inclined plane. Okay, so in this situation, somebody get out a calculator. Let's actually calculate some numbers. So in my force parallel is going to equal my Fg, which is 10 newtons in this case, times the sine of 30 degrees. So somebody take 10 newtons times the sine of 30. I think you get 5.
Yeah, 5.
Okay? And then my normal force is going to be 10 newtons times the cosine of 30 degrees. That's 8 something.
8.66.
8.66. Make sure your calculators are not in radian mode. Okay? Your calculators have to be in degree mode. Okay? Now, at this point, we need to make a decision on this problem. We need to make a decision. And I don't care what that decision is, but we need to make a decision. So here's what we've got. We have a 10 Newton force acting down. Okay, we know that. That's my gravitational force. Okay? Boom, 10 Newton, straight down. Here we go. Now, I'm going to show you 2 ways you can draw your normal force depending upon your perspective. If you're into triangles, you can draw your force normal and your force parallel like this, where your normal force is drawn at a right angle to the incline. Your force parallel, oddly enough, is parallel with it because that's what makes it move down. Okay, that's what we call it, force parallel, because it's parallel with the surface. It's not the most clever title in the world, but it works. Okay, so we have a force parallel and then the force normal. Okay, that's one option. So if you're into triangles, you're going, Mr. Brookhamp, I was president of the Triangle Club in high school. Cool. Draw it as triangle. There you go. Now your other option, some people like this because it's actually more representative of what is actually happening. Your other option is that you draw it as like a free body diagram, and you draw that force normal going straight up from the surface, and then you draw your force parallel coming down like this. So some people like this because it's easier for them to see, oh, this is actually how the forces are acting. That table is providing a normal force that's going up like this. There is a force parallel that's acting straight down along that surface, okay? I don't care which one you draw, okay? I don't care. I always do this one because it's easier for me to see how they're acting, okay? If you like triangles, draw it like this. I don't care. Pick one, okay? Just pick the one that makes the most sense to you. But here's what you have to do. That normal force is not acting straight up, okay? That normal force, you have to draw it at a right angle to the surface, okay? You all are used to drawing normal forces straight up because you all are used to having flat surfaces, okay? This isn't a flat surface. This is at an angle, okay? So I've got gravity going straight down. The normal force is at a right angle to the surface. Parallel, as the name implies, is going parallel with the surface, okay? Got that? We're good. Good, got it, fantastic. Now, here's the decision that we have to make. And there is no right or wrong decision to this. What you have to decide is the force parallel. Do you want that acting down to be a positive or negative value? Peyton, do you want that force parallel, which is 5 newtons, do you want downhill to be positive or do you want downhill to be negative?
Negative.
Okay, fine. In the Peyton Cartesian system of inclined planes, downhill is going to be defined as being a negative value. Okay? It's cool, right? Now, Adana might have said, Mr. Brookhamp, I'm just saying you could have, okay? She could have gone, oh, man, I like downhill. I want downhill to be positive. Fine, okay? There is no right or wrong answer. But once you pick a system within the confines of a problem, you have to define everything like that. So if we're going to go with the Peyton system, okay, if we're going to go with the Peyton system, anything going down that inclined plane is going to be a negative value. Anything going up that inclined plane is going to be a positive value. Okay, that's it. Downhill is negative, uphill is positive. If you're Adana and you want to make downhill positive, fine. Downhill is positive, anything going up the hill is negative. Okay? Don't care. I don't care. You pick whatever system that you want. But once you pick your gate, once you pick your system, that's what you've got. Now, let's talk about force parallel. Force parallel always acts down the inclined plane. It isn't necessarily always negative, depending upon how you set up your system. But your force parallel always acts down the inclined plane. If you go out to Colorado and you go skiing, when you get off the lift at the top of the mountain, you never have to worry about gravity pushing you up the hill. Okay? Gravity is never going to push you up the hill. Mother Nature goes, oh, that's way too much effort. No, not going to do that. Mother Nature goes, fine, you're up the hill. I'm happy for you. Enjoy the view. But I'm going to make you go down the hill. Okay? So force parallel never, ever, 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 never, 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 never goes up the hill. Force parallel always goes down the hill. Gravity is never going to push you up the hill. And if you define downhill as being negative, that's going to be a negative number. Okay, now, as the angle increases, so let's say that's at 30 degrees. So we've got this cool little deal here. that measures a couple of things. So, and it's got a scale down in here at the little digital scale. So I'll turn that on. And this compression spring scale over here measures the amount of force acting parallel with the system. Okay? So oddly enough, right now, when I turn this on, the scale is reading about 8.5 grams. So this thing is completely flat at this point. Okay? The scale is reading 8.5 grams. There is no force parallel because I'm on a flat surface. Now, what I'm going to do is I'm going to take this and up here, and I'm going to lift it up. Okay? So as I lift this thing up, what do you think is going to happen to the reading on the scale that balances out the force of gravity? Right now it's at 9.7 newtons, or excuse me, 9.7 grams. Okay? It's just measuring in grams. So as I lift that up, what do you think is going to happen to that reading that's measuring the downward pull of gravity acting into the scale? Is it going to increase, decrease, or stay the same? Tyler?
Increase.
So as I lift it higher, do you think that scale, that might go up to like 10, 12, something like that? So here's what we've got.
Wait,
Hold on. So I've got a little scale here. Here's the cart that's sitting on top of it. And right now, that scale is reading 9.70 grams. And then I've got another scale here, which is measuring the force parallel, and that scale is reading 0. So, well, I'm going to lift this thing up, okay? And I'm going to tilt this higher and higher and higher. So the question being is, what's going to happen to the reading on that scale?
so I thought you were talking about the other,
No, I'm talking about the digital scale.
that would decrease.
Fantastic. Is gravity getting weaker?
No.
What's happening?
Like angle is decreasing the force normal.
Oh, beautiful answer. Okay? So what's going to happen is that I lift this up, and let's go up to, I don't know, we're at about 30 degrees. Okay? So let's lock that in place at 30 degrees. So if I lock this thing at 30 degrees, the reading on that scale, when I lift it up to 30 degrees, has dropped to 7.56 grams. Okay? Now, gravity is still pulling it down. Okay? But there's less of that force that's acting in the direction that the scale has to balance out. But what's happened to the reading on this scale is that it's gone up to about 0.25 newtons. So this scale is measuring the force parallel. This scale is measuring how hard the scale has to work to keep that from sliding down. So as I go a little bit higher, so now if I go up to, let's say, 60 degrees, okay? So if I go all the way up to 60 degrees, the reading on the scale has dropped to 2.3 grams. So now if I'm up here like at 60 degrees, that's dropped to 2.3 grams, but this scale is up to about 0.6 newtons. So as I go higher and higher and higher, listen to me. Gravity is still pulling down with the exact same amount of force. Gravity is still acting straight down. But it's exactly what Tyler said. As it goes higher, my normal force is going to become smaller because less and less and less of that gravity is acting into the surface. More and more of it is acting parallel with the surface. Now, if I go all the way in an extreme case, I'm going to go all the way to 90 degrees. Okay? Boom. I'm at 90 degrees. At 90 degrees, the reading on the scale, on this scale, is 0. Why? Why is that reading on the scale 0? how much of that weight is acting into that surface? None of it. It's all parallel. Okay? So as you go steeper and steeper and steeper, your force parallel is going to get bigger and bigger and bigger, but your force normal is going to become smaller and smaller and smaller. Now, if I reverse it, and I bring that back down to a flat surface, now all of that is normal force and none of it's parallel force. Okay? Got that idea? All right. So now what can we do with all this information? So what I'm going to do is I'm going to play out some different scenarios. Okay? Scenario number one, and we're going to use the same block every time so that we don't have to redo the calculations. Okay? Scenario number one, I'm going to put this thing on a 30-degree angle. Here's my mass, 1.02 kilograms. And there is no friction. Okay? It's friction on the surface. There is no friction. And I'm just going to let go. Okay? And I want to calculate the acceleration of the block. Okay? So imagine this, if you will. That I'm going to put this thing at a 30-degree angle, which is about like yay. I'm going to do it like this, okay, where there's no friction, and I'm going to let go of it, and I want to figure out what's the acceleration. Now, obviously, what does my acceleration have to be greater than? 0, right? It has to be bigger than 0. Is it going to be 9.8 meters per second squared? No, because we're not vertical, right? So my acceleration has to be somewhere between 0 and 9.8, okay? 30-degree angle. So here's what you're going to do. What I would recommend is that you set up a chart. And at the bottom of the chart, we're still going to put force net. Now, since I let go of that, and it begins to accelerate, what do you know my net force does not equal? 0. I know I have to have a net force, because when I let go of this thing, it began to accelerate. So I know my net force is not 0. Now, we're going to stick with the Peyton system. Downhill is defined as being negative. So is my net force, because it's accelerating down the hill, is my net force going to be a positive or negative number, Peyton?
Can you repeat that?
When I let go of it, is my net force going to be a positive or negative number? Negative, because you define downhill as being negative. Okay? So I know this acceleration is going to be, say, some negative number. I don't know what it is. I just know it's going to be a negative number. Now, this is where we're going to add another layer to this puzzle. Okay? We can still have force applied. Okay? Just like we're used to. We can still have force opposing, which could be friction, something like that. But now we're going to have a third layer to this. And that's going to be force parallel. Okay? So it's the exact same concept. The only thing that we're going to add now is some force parallel to the problem. Okay? So here's the story. I'm going to have this like this. Frictionless surface. I'm going to let go of it. Am I pushing, pulling? Are the rockets involved at all? Is there any applied force? Nothing. My applied force is 0 newtons. I'm not pushing it. I'm not pulling it. There's no propellers, blades, sails, squirrels, nothing. Okay? My applied force is just 0. Now, it's a frictionless surface. So what's my opposing force going to be? 0. I got nothing there. Okay? Now, because of the Peyton system, my force parallel is going to be negative 5 newtons. Okay? So check my math, and if I take 0 plus 0 plus negative 5, I get negative 5 newtons. Right? So because the force parallel is the only game in town, so Only game in town. That's my net force. That's it. Now, knowing that that's my net force is -5 newtons, and the mass is 1.02 kilograms. That's my net force, -5 newtons. I got a mass of 1.02 kilograms. How am I going to get my acceleration? Adana.
Divide the force by the mass.
Yeah, I'm going to take that net force of -5 newtons, divide that by 1.02 kilograms. So my acceleration is still going to be net force divided by mass. There's nothing new. It's the exact same equation. It's still net force divided by mass. And if you take a -5 newtons, Devin Walter White, and divide that by 1.02 kilograms, what do you get? -4 something.
Negative 4.9.
Meters per second squared. Okay? There you go. It's the exact same idea. Net force divided by mass gets you acceleration. Same thing. Okay? Cool with this. Now, exact same inclined plane. Still no friction. Okay? Still a friction of the surface. Still 30 degrees because I don't want to redo any more calculations. Okay? Still 30 degrees. I still have FG. I still have my force parallel. I still have my force normal. So when I ask you to draw vector diagrams on inclined planes, these are the three that you always draw. Gravity, parallel, force normal. Bread and butter. Okay? Those never change. Bread and butter. Now, I want to calculate how much force it's going to take, okay, to pull it up the hill at a constant velocity. Okay? So here's the setup. 30-degree angle, frictionless inclined plane. I'm going to push this thing up the hill at a constant velocity. So as soon as you see the words constant velocity, Angel, what is my net force going to equal? 0. So I'm going to go back to my chart. I'm going to have force applied, force opposing, force parallel, force net. Same layers of cake. Now I want my net force to equal 0 newtons because I don't want it to accelerate. I want it to move. I just don't want it to accelerate. So my force parallel is -5 newtons. I have no opposing force because it's still frictionless. So what does my applied force have to equal? 5 newtons. So now, if I take +5 plus -5, I get 0. So from a vector standpoint, now I'm going to have this applied force going up the hill of 5 newtons, which balances out that force parallel of -5 newtons. Now, my normal force is there. Okay, it's 8.66. I don't worry about that because that isn't in the direction of motion. Gravity is pulling down at 10 newtons. Don't care. Not in the direction of motion. So the only thing I'm going to worry about is the forces that are acting to cause motion. The normal force is there. It's cool. It's important. Okay, if I don't have the normal force, I fall straight through the center of the earth. The normal force is there. It's important. It's just not in the direction of motion. So when I talk about the sum of the forces, all I'm talking about are the forces that can cause motion on the inclined plane. Cool. Set that down. Know you've been sitting. Stand up. Take a... Exact same inclined plane. Still the same block. Weighs 10 newtons. Force parallel is still -5 newtons. The normal force is still 8.66 newtons. But now there's friction. Okay? Now there's friction. So it would be like me, instead of having this thing with the wheel sides down. Now, I'm going to have it go like this. So, you all intuitively understand this. When am I going to have the greater acceleration? Wheel sides down or wheel sides up? When am I going to have a bigger acceleration? Wheels down. Why?
Because there's no friction.
There's no friction. Okay? Now, this is an odd situation. Up to this point, we've talked about the frictional mafia as one operational realm, and we've talked about the gravity mafia in another operational realm. Okay? This is the one situation where the mafias are combining together. Okay? So in this situation, we have to deal with the gravity mafia and the frictional mafia. Now, when I let go of this, when I let go of it and it begins to slide down the hill, which direction does my frictional force act? Up the hill or down the hill? So I'm like this, right? I'm going to let go of it. It's going to go like this. Which direction is my frictional force going to act? Up the hill, down the hill?
Up.
Cooper, you say up the hill. Carson, you say up the hill. Why does it act up the hill?
Because
Connor. Connor. Why did you point up the hill?
Because it acts opposite to motion.
Yeah, it acts in the opposite direction of motion. Okay? So, my forced friction, now listen to me, listen to me, listen to me. Your forced friction does not always act up the hill. Your forced friction just always acts in the opposite direction of motion. Okay? Now, if we go with the Peyton system, which we are, okay, my force parallel is going to be negative 5 newtons. What's going to be the sign of my frictional force? Positive or negative? Positive, right? Because it's acting up the hill, right? Because Peyton decided to make down the hill negative, so my frictional force is going to act up the hill. Now, to calculate the force friction, you go to the same equation that we have done 100 times. Okay, it's the exact same idea. Now, because Alexia said she wanted mu to be 0.0115. That's our coefficient of friction. So we're going to take 0.0115, has no units because it's just a coefficient. Now, on the normal force, I'm not going to use the 10 newtons, okay? Don't use the weight of the block. You have to use the normal force, which in this case is going to be 8.66 newtons. So somebody take 0.115 times 8.66 newtons. Let me know what you get. .8 something, I'm guessing. Room full of calculators.
0.996.
0.996?
Yeah.
There's no way.
yeah, there's way.
0.115 times 8.66?
Yeah.
Okay. All right, what was it?
0.996.
0.996, okay. All right. About 1 newton, okay? I thought that would be solid. Okay. Now, so this pointing up the hill is 0.996 newtons. So this is where the two mafias are going to have a turf war. Okay? There's a turf war involved. The gravity mafia is going, we want you to go down the hill. Okay? And the gravity mafia is pulling at negative 5 newtons. The frictional mafia is pulling up the hill going, no, Tony, don't go. Okay? So the gravity mafia is pulling Tony down the hill with the force of 5 newtons. The frictional mafia is pulling Tony up the hill with 1 newton, about. Okay? So who's going to win? The gravity mafia or the frictional mafia? Gravity mafia is going to win. Okay? By how much? By about what? Negative 4 newtons. Okay? So if there's no frictional mafia, all the gravity mafia takes all 5 newtons and makes it accelerate. Once there's friction, the frictional mafia is working against that, going, Tony, stay. The gravity mafia is going, no, I really want you to go. So Tony feels more of the pull towards the gravity mafia and less of the pull towards the frictional mafia, so he's going to go in the direction of the gravity mafia. So we're going to set up the exact same chart. Okay? Force applied, force opposing, force parallel, force net. Okay? That's what you got. Now, there is no applied force. We're not pushing it. We're not pulling it. There's nothing involved like that. There's no rockets. My applied force is 0 newtons. Okay? 0. That's it. Now, my opposing force is going to be the frictional. That's going to be my frictional mafia, which I incorrectly calculated, but it's 0.996 newtons. Okay? My force parallel, because of the patent system, is negative 5 newtons. Okay? So imagine this. I got a negative 5 newton force going down. I got a 1 newton force acting up. So the difference between those two is going to be my net force. It's the exact same ideas we've been talking about. Okay? Oh, right, there's an imbalanced force. Hey, I'm going to accelerate, right? So I'm not even going to try and do the mental math. So somebody take 0.996 plus a negative 5, and let me know what you get.
Negative 4.004.
0.004, okay? Newtons, that's cool, right? Now, how am I going to get my acceleration? What am I going to divide that by? Mass of the system, right? Force net equals mass times acceleration. So I'm going to take, gravity is strong today. So I'm going to somebody take negative 4.004 newtons and divide that by 1.02 kilograms, and let me know what you get.
Negative 3.93.
Meters per second squared. Now, look at this. When I had no friction, when there was no friction at all, my acceleration was negative 4.9 meters per second squared. When I had no friction, my acceleration was negative 4.9. Now there is friction. What's happened to my acceleration? It's become smaller. Why? What do you have? What's working against you? Yeah, the frictional mafia. The frictional mafia is working against you. The gravitational mafia is still pulling you down. You have a smaller net force, you have a smaller acceleration. Now, will you get an acceleration every time you put an object on an inclined plane? If you put an object on an inclined plane, will it always accelerate? Connor, you shake your head no. Why?
Because sometimes friction is greater than the parallel force.
Ah, sometimes the frictional mafia is stronger. So I take this, right, and I put it like this, and I lift it up. Okay? Is the gravity mafia trying to pull it down? Yes, but what's happening? The frictional mafia is stronger, right? Now, if I go steeper, then what happens? The gravity mafia becomes stronger than the frictional mafia. But if I put something on an inclined plane, and the frictional force is bigger than the force parallel, you're just not going to accelerate. Okay? So this is a classic example of just because a force is acting on a system doesn't mean that it's going to accelerate. Now we have one last problem, and then we're done. And we don't even have to calculate anything new. So I'm going to go back to that 30-degree angle, the same block. Mass is still 1.02 kilograms. Gravity is still 10 newtons. The normal force is still 8.66 newtons. The force parallel is still negative 5 newtons. Okay? Everything is the same. Okay? Everything is the same. Mu is still 0.115. Okay? That's still the same. Now there's still friction now. Okay, we still have friction. But now here's what I want to know. I want to know how much force it's going to take to visualize this. I want to know how much force it's going to take to push it up the hill at a constant velocity. Okay? So now I'm going to push it up the hill at a constant velocity. So to push it up the hill at a constant velocity. Now, constant velocity. All my forces are going to add up to 0. So if I come over here and I make my chart, now I've got all things in play. I've got my force applied, I have my force opposing, I have my force parallel, and I have my net force. What is my net force going to equal? 0. Now my force parallel is -5 newtons. Okay, that's never going to change. It's -5 newtons. Boom. 30-degree angle of that mass, -5. Boom. Now here's the interesting thing. I'm going to push it up the hill. Which direction does friction act? I'm pushing it up the hill. Which direction is friction going to act? Down the hill or up the hill? Down. Friction is now going to act down the hill. So now what do I have to do with the sign of friction? Change it to a negative value. Because now friction is going to be a negative value. Okay? Same value, but now I've got to make it negative. This is why I said it's so important that how you define your system. So in this situation, that frictional force, instead of being a positive 0.996, is going to be negative 0.996. Now, my applied force has to overcome two things. It has to overcome the frictional force. Now the frictional mafia and the gravity mafia are working together. Okay? Now they've combined forces. Okay? Because they're going, oh, you want to push it up? Oh, Okay? So now they're going, you got to pay both of us. Okay? Because now they've like joined teams. Now it's like this mafia super group, right? Because now both of them are going, oh, Tony, no, don't go up the hill, man. No, don't go. Because the frictional mafia is going, no, man, you're in the opposite direction. Gravity's mafia going, no, man, we're going to pull you down the hill. So I've got to overcome both of those forces. So now my applied force has to be, oddly enough, 5.996 newtons. So therefore, my net force adds up to equal to 0, and I don't accelerate. So that's why I said the frictional force can be positive or negative depending upon how you choose your system. Okay? But what's always going to be true of force friction, that is just as always in the opposite direction of motion. So, if you've ever watched like the Winter Olympics, most of the Winter Olympics, you could also be named, like, I'm biased, but a lot of Winter Olympic sports are like the force parallel games. Okay, if you think about it, bobsled, luge, downhill skiing, okay? It's all about force parallel. Okay, it is. Now, if you want to win the downhill race in the bobsled team, everybody's going down the exact same slope. Everybody has the same capacity to accelerate down the hill. If you're the bobsled team, what are you trying to minimize to make your fastest time? What do you want to minimize if you want to have a fast time going down the hill? Your applied force or your opposing force? Yeah, you want to minimize the friction. This is why they're all about aerodynamics. Watch the guys that's downhill ski. They go into that tough position. They wear very slick plastic so that they can cut through the air to minimize that opposing force. Okay? You're never going to see a guy going, that's like, hey, what do you do? I'm going to try something new on the downhill. I'm going to hold up a sheet of plywood when I go down the hill. See, you're going to lose horribly. Okay? You hold up that big sheet of plywood, now you have all that wind resistance? No. Okay? Winter Olympics, force parallel games. Okay, stop that. Okay, So on 1 and 2, all I'm asking you to do is do the calculations. You have a 2.8 kilogram box, rests at a 20-degree angle. Determine the gravitational force, force normal, and force parallel. Okay? Just get numbers. Don't worry about making any calculation on 1 or 2 negative. Okay? Just give me the numbers. 1 is at 20 degrees. And I want to take the exact same block and I want to lift it to 60 degrees. Now, when you get to number 4, okay, I want to put a 1.2 kilogram box on a 20-degree hill. In your system, uphill is defined as positive or negative, and downhill is defined as the other one. I don't care how you answer number 4, okay? If you want to make downhill negative, fine. If you want to make downhill positive, fine. I don't care. But once you pick that system, you got to stick with it, okay? That's just the rule. So what's going to happen on number 5, I'm going to calculate the force parallel acting to accelerate the box down the hill. So on any of these where there is an inclined plane, on those I want you to draw the forces acting on the system. So on all of these, there's going to be 4 of them. On number 5, number 7, number 9, and number 10. So when you see this, okay, put the box, whatever it is, and you're going to draw all the forces acting on that. At a minimum, there is going to be 3 of them, okay? Gravity, normal, force parallel. At a minimum, there's going to be 3. So, force parallel acting to accelerate it down the hill. What's the acceleration of the box without friction? Okay, if you want to set up a chart, I recommend that. Now, when you get to number 7, now we're going to introduce friction. Coefficient of friction is 0.28. What's the force friction? In which direction does it act, up or down? So in number 7, now you're going to have the same inclined plane, but now there's going to be friction. When you get to number 8, what's the net force and the acceleration once the box is factored in? When you get to number 9, on the back side, you have a 1.34 kilogram box. You're moving it up the inclined plane at a constant velocity. You don't know how much force it's going to take. When you get to number 10, still at a constant velocity, but now there's friction. All right, I'm done. You're on your own. Have a good weekend.